welcome to the first TILOS HDSI colloquium of the year. So it's good to see that the room is full. People are excited. Yeah, so it's great to have Adam Klivans to do the first talk. And Adam has done a lot of work on theoretical machine learning. He is the director of our sister IF Institute on the Foundations of Machine Learning. Oh, I said it correctly. Institute on the Foundations of Machine for Foundations of Machine Learning. Let me be quite precise. In any case, yeah, Adam did his PhD at MIT, and then he spent some time at Toyota Institute in Chicago, where we actually first met. In those prehistoric times, you know, before we knew what AI was and all that other stuff. And then he's been faculty at UT Austin for 20 years. Wow. Yeah, let's welcome Adam.
It's great to be here. I've actually never been to UCSD before. I've been to San Diego before, but thanks for inviting me, Misha and Yuzu, and you know, happy to be here. Sanjoy and I were PC chairs in 2008. Is that right? You were having a baby at the time, I remember. So that was exciting. And at TTI, that was an interesting group at TTI. It was me, Adam Kalai was there. John Langford was there, Sham Kakade was there for a little bit, Yishai Mansour was there. So yeah, that was fun, and actually I did some work there that I will refer to in this talk. Kind of finally solved some things in only 20 years. I've given this talk a couple of times. Yoav has seen a fair, like maybe 70% of it. Where are you, Yoav? Let's see. Oh yeah, he saw maybe 70% of it in Switzerland, but I have added new stuff since then. I mean, the work is ongoing, and I will mention that during the talk, so it would be a complete waste of your time. I do want to say that this is joint work with my student, Kostas Stavropoulos, who's graduating this year, and Arsen Vasilyan, who's my postdoc, and they're just amazing researchers, and it's you know. It's been an incredibly productive time working with them, and they've done, you know, all credit to them for this work. The main thing that I want to talk about, and I know that many of you are interested in, is generalization. And I want to make just so we're all on the same page. Typically, when we talk about generalization in a learning algorithm, what comes to mind is that you see training samples from some distribution D. You know, this is, you see training samples, labeled samples from your distribution D. Think about classification, you know, Boolean classification. Then you output some classifier H. And with the following criterion, you want that, you know, when you draw a new sample from D, that the probability that H makes a mistake is small. Okay, this has been the goal of so much of learning theory for decades. And the thing that I want to be on, you know, on the same page with everyone is that typically, the vast majority of the time, we just assume that the training distribution that you see samples from is the same as the test distribution. And if you perform well with respect to the test distribution, we say that your classifier generalizes. And I want to make a controversial point that this is the wrong notion, that this isn't generalization. I want to make the point that, you know, maybe we should call this mimicry or imitation, because detrain versus, you know, equaling detest is a huge assumption. And I just want to point out that despite sort of decades of you know, theoretical and experimental work in this scenario when detrain equals detest, kind of amazingly, we know very little for the case when detrain does not equal detest. Even, you know, theoretically, certainly experimentally, you know, and I'll talk about that in just a second. So I kind of want to make several points during this talk. One is that this notion of generalization where D-train equals D-test is wrong. And the other is that there is a whole kind of field of coming up with efficient algorithms for handling the case when D-train does not equal D-test that my colleagues and I have been working on for the last 2 years. I think it's a very important area, and I think there's still a lot to do there, and I want to give you a feel for kind of what you can do in this scenario. Before I do that, I want to take just a little detour towards protein engineering, which, by the way, how much time do I have? Like an hour? Stop at 12 or something? Okay, great. Put a timer on myself. And because I've been working in protein engineering, AI for protein engineering, I have a whole separate group that does that. Very interesting set of problems. Very well suited to machine learning. And typically what happens in protein engineering is you have these amino acids. You have a protein, which is a sequence, it's a sequence of amino acids. You don't know any biology or chemistry, it's fine. There are 20 amino acids. Here's a sequence, K stands for lysine, S stands for serine. And the goal in a lot of AI for protein engineering is to figure out what happens if I make a mutation on this protein. If I change one of the amino acid residues from lysine to serine, how does it affect the protein? And it turns out that what happens in this space, I think it's very interesting, especially if you're into language models, is that one of the most important protein language models that was developed is simply a BERT-style training on the space of all protein sequences. So you take like 600 million protein sequences, and you mask out, for each one, you mask out 15% of the residues. And then you ask a classifier that you're training, like, what did I just mask out? It's like a BERT type training for a language model. And it tries to predict what residues are appearing in those positions. You have a loss function. You train a model to do this with 600 million residues. Someone did this. You get a model called ESM2. Has anyone used ESM2? No one here has used it. Okay, nobody does. It's a very, very popular language model. It's developed in Meta. And if you talk to anybody who does AI for proteins, they will tell you like, oh yeah, we use ESM2, and there are many people, my group also works to improve these models. So that's fine, but it turns out that this notion of accuracy, like how well did you actually predict what residues were there, is the totally wrong metric for doing protein engineering. And the reason why, if you think about it, is the goal of protein engineering is to come up with proteins that don't exist in nature. They're new. If you had a model that was 100% accurate with respect to predicting residues that have been masked out, then you're just always going to get whenever you take a protein and you want to engineer it, you mask out a couple positions, your model is always going to give you something that was in nature. And so your model is actually useless. So you talk to people who do protein engineering and they'll say, oh, we came up with a model that beats ESM2. It has a higher wild type accuracy. And you're like, okay, cool. What if I gave you a model that was 100% accurate? Would that be good? And you explain that to me. Like, oh yeah, that wouldn't be good. And you're like, well, wait a minute. Do you want like an 89% wild type accuracy? Or should it be 87? Or like, where exactly is the cutoff? And they get very confused and annoyed at you. And for biologists, I will just say that when you say generalization, they are always thinking out of distribution. Like if you tell them, yeah, I have this model and it performs well, assuming the test set comes from the same distribution as the training set, they'll be like, but look at distribution. And then I thinking more about this, I realized, well, they're right. And it's not just biochemistry. Okay, here's a more like fundamental problem that's sort of easier to understand. Imagine that you are doing AI for health, and you want to detect if an MRI scan indicates cancer. So what happens today, you build a foundation model from a bunch of known MRI scans that have been hand labeled by experts. So that's your labeled training set. You build your foundation model on some population of patients, and then you're ready to deploy it on a new distribution of patients. And that corresponds to an unlabeled test set because it's a new set of patients you need to predict whether or not their skin is cancerous. It's a new distribution of patients. Like, how do you have any insight at all as to whether or not that's close to your training distribution? And I truly believe that this is the main obstacle for kind of deploying AI systems for health in the real world, is that we just don't trust them. And we have no ways of kind of quantitatively, we have no theory for this. We have no quantitative way to understand this. If you ask people who work on AI, anybody here work on AI for help, they'll say, well, okay, I know that I didn't train on my test set because my test set came from people in Ohio. My training set came from people in Illinois. You're like, well, okay, why does that mean? How do you quantify the shift in distribution? I don't know. Very strange. But very important problem, talk about trustworthy machine learning. This is it. Another kind of interesting case where distribution shift pops up is when you want to train generative models for noise. So some of the things that my colleagues and I have been working on in the context of coming up with generative models for proteins, it's like, when you come up with a generative model for images, in some sense you're in good shape because you have a training set of very clean images to work from. Okay? Imagine you want to come up with a generative model for something that exists in nature, like proteins or molecules. Every single point in your training set is noisy because you had to use some instrumentation, like X-ray crystallography, to actually figure out what the structure looks like. So inherently, every point in your training set has noise. So you want to build a generative model, and you want that generative model to output clean-looking structures or very sharp resolution, high-resolution images of molecules. But you never gave it a single sharp structure. You never gave it a single high resolution image because the data set itself is inherently noisy. And so you want the model to shift from one distribution, like namely these noisy images, to something clean. We actually have a method called ambient diffusion. Yannis Daris really leads the work on this. And this is an actual result. So you can train on images where 90% of the pixels have just been blacked out. So your model never sees a clean image. And then you can train the generative model in an interesting way so that when it outputs, the output of the generative model is actually clean faces. Okay. Kind of surprising that you can do this and surprised us, but we're using that now for various applications in AI for science. Okay, so just another example where distribution shift pops up. And as I said, we're trying to build the foundations of the theory of learning with distribution shift with an emphasis on coming up with algorithms, coming up with like an algorithmic toolkit. So I want to tell you about this new model, give you some toy examples for the type of algorithms that we've come up with, and then give you an inkling of sort of the more sophisticated algorithms that we've come up with, okay? Right, so the model that we came up with is something called TDS learning. And I'm going to assume that everyone is familiar with pack learning or epsilon delta learning. How many people have heard of pack learning or epsilon delta learning? Raise your hand. Okay. Does anyone want me to go over epsilon delta or pack learning? I can easily add a slide in on the fly. Oh, you would like that? Okay, cool. So, oh, right. Should be easy. It's not. Oh, maybe it's this thing is.
There's also a whiteboard you can use.
Oh, really? Yeah, maybe I should. Oh, there we go. Okay, it worked. So in pack learning, okay, you have some class of functions that you're trying to learn. So this is some class of unknown functions. You can think of it as, say, neural networks. Okay, and then the learner, there's some underlying distribution D on your input space with some labels. So, everything's Boolean classification, so it's +1, -1. And then the learner draws samples from D, and they're labeled by some function C and C. So there's some ground truth function C, and you're trying to figure out what is this ground truth function. The learner draws a bunch of samples from D, and they're labeled according to some ground truth function. And then the goal here is to output a classifier H, such that the probability when you draw a new sample from D, that H of X does not equal the ground truth is at most epsilon. So you want the H that you output to be very, very close to the ground truth. And this should happen with high probability, so with probability of at least 1 - delta. I mean, you could get unlucky and just keep seeing, as you draw these samples, maybe you see the same sample over and over and over again. Then you're not going to be able to do any learning because you just keep seeing that one sample. So there has to be some probability of failure. So what you want to do is output a classifier such that with high probability, your classifier is close to the ground truth. And the key thing here is that, again, the test distribution, what you're testing on D, is the same as you drew samples from. Okay, so that's pack learning, excellent. Feel free to interrupt me with any questions. Okay, how many people are familiar with domain adaptation? Yeah, it's usually far less. This is what I find when I give this talk. So I am going to tell everybody what domain adaptation is a field of learning with distribution shift. It's been around for, I don't know, 25 years, 30 years, something like that. It's been around for a while. And this model is more representative of some of the examples that I talked about at the beginning of this talk. In domain adaptation, again, you have a training distribution D, or sometimes I call it D train. And again, you get to see samples, labeled samples of your training distribution. And then there's this test distribution D prime, but the learner only gets, it is a distribution over x cross minus 1 and 1, but the learner only sees the marginal, so it doesn't see any labels. Okay, so for the training distribution, you get to see instances x and labels y. For the test distribution, you only get to see unlabeled x. You don't get to see any labels. Which makes sense. Like if I have a new population of patients, I don't know initially if they have cancer or not. I have to label that myself. And the goal this time is to output a classifier H that is accurate. So the probability it makes a mistake with respect to a new label is small, but the accuracy is with respect to D prime, the test distribution. Okay, makes sense? Interrupt, feel free to interrupt. So this is domain adaptation. All right. Now, there is this quantity called lambda, which we have to deal with. If you don't like lambda, you can assume lambda is 0. That means that there is a ground truth function that labels everything correctly in both the training distribution and the test distribution. And that is called covariate shift. It's still a heavily studied scenario. So lambda equals 0 means there's a ground truth function labeling everything in D-train and D-test correct. But typically the way we measure the accuracy of the best fitting classifier is we say, okay, look at all functions from your class C and take the error of that element of F with respect to your training distribution plus the error of F with respect to the test distribution. And minimize over all functions in your class. That's called lambda. If you're familiar with like agnostic learning, this is similar to the OPT opt quantity. But in domain adaptation, it is lambda. Lambda measures the error of the best fitting classifier from C with respect to both the training and the test distribution. Okay, and that's what we have to compete against. Yeah, and so the goal is to output H such that the error of H on the test distribution, I'll cut you some slack and let you output something that's like order lambda plus epsilon. Again, if lambda is 0, it's still a very interesting case. And now I have the pleasure of telling you basically every result in domain adaptation over the last 20 to 25 years. They're all generalization bounds. And the way that they work, so there's a generalization bound, and it says, look, if you give me a classifier H, what I'm really interested in is the error of H on D prime. And the error of H on D prime, you can upper bound as the training error. Okay, that makes sense. Plus lambda, that is unavoidable. We can prove that. Plus, and I think this is intuitive, some notion of distance between D and D prime. How much D prime has shifted from D. Okay? Basically, every result from the last 20 years of domain adaptation is a bound of this form. Maybe the notion of distance between D and D prime changes and varies according to the paper that's being written, but this is basically it. And well, let me just say this. I'll come back to that in a second, but these bounds, I don't want to say they're useless bounds, because that would not be nice, but let me say they're not useful bounds. And the reason why they're not useful is that there is no computationally efficient way for estimating or testing this notion of distance between D and D prime. Okay, so imagine that you've downloaded your favorite domain adaptation paper because you have a distribution shift problem. Like you actually want to apply one of these generalization bounds. Like you actually want to apply it to your particular problem in the real world. And you say, okay, I built my classifier. I want to figure out its error with respect to D prime. But you downloaded your paper and it says, well, just estimate this. Okay, no problem. I know my training loss. Assume lambda is 0 for right now. Ignore that. And then I have to compute distance between D and D prime. I can't estimate it. So the bound really tells me nothing. I have no way of actually applying or understanding. The bound tells me nothing because it can't be estimated in a computational way. Yeah.
Can I ask a more basic thing?
Yes.
Is lambda the best thing? Like, is
Did you just pop in and miss that? Yeah.
yeah,
Lambda is this. It's the error.
yes, but
yeah.
why do I care about the error from D? Should it not just like, should I not worry about only opt for D prime?
No. So the reason why you have to pay lambda is the following simple scenario. Like you get your labels from your training set, right? Your test set, imagine a test distribution that's the same as your training set, except all the labels are flipped. But you can't know that. So that's what lambda is kind of capturing. Like you always have to potentially pay the fact that you don't know whether D prime is going to keep the same labels that you have on D train, or it's going to flip those. So there's simple examples that show that like basically, and you might even say, well, why is it a max or something? You can prove it has to be the sum.
Right. Like, so what I'm missing is why do I have to have put error in D? Why should I not just?
Yeah. So
that's the.
Yeah, you can come up with these examples where you really do have to pay error in D. There are these little counterexamples where because if you formally have this model, it has to handle both cases. We can talk about it offline, but yeah, you do have to pay it. Yeah.
I guess if D prime is equal to D, your algorithm should still work, right? It should work if there is no transfer, right? In that case, it's
Yeah.
clear.
Yeah. I mean, yeah, that's true too. Like if D prime equals D, then certainly your classifier has to still true. So it shouldn't get worse, yeah. But there are these simple, you have to pay the sum, like you have to pay it. Yeah.
Why can't we estimate that distance again?
Yeah, I'll talk about that in a second.
If we have samples from.
I'll talk about that in a second. I will get to that. Yeah, good question. Okay. And I just want to say, maybe even more controversially, like a word on assumptions, like distribution assumptions are everywhere. So like, ARIA works on compressed sensing. But you only know if your algorithm in compressed sensing worked if your design matrix was like RE or RIP, and that's NP hard to test. So you don't even know if your compressed sensing algorithm worked. Maybe you want to come up with an algorithm that works for learning neural networks, but it only works with respect to Gaussian marginals. Well, that's not something you can test. So you don't know if your algorithm worked. And these are sort of inherent problems with average case analysis. What we take for granted in people who work in TCS, like me, what we take for granted is that typically we work in a worst case analysis setting where you prove that an algorithm works on all instances. And what that means is that when you run your algorithm, you actually have a certificate that your algorithm worked because you proved that it worked for all instances. And in the average case, like the instances are coming from some distribution that you assumed. So somehow you have to test that they came from this distribution. That's what we're going to do in this talk. And I want to emphasize that in all of the results that I talked about today, we will not be making assumptions on D-test. Okay? I'm cool with making assumptions on D-train because you yourself are creating the training set usually when you build a foundation model and you have a lot of control over it. But D-test, no. Okay. And I guess since I skipped this, I'll just quickly say that the most common notion of distance that people look at in domain adaptation is this notion of discrepancy distance. And what it measures is you take any pair of functions from the underlying concept class, and you ask like, how much did they differ with respect to D versus how much they differed with respect to D prime. And if this is large, that means that there has been distribution shift. If this is small, then it means you can trust your classifier that you trained on because the difference between the ground truth on D prime is actually also going to be small. But from a TCS perspective, what this means is that D prime is actually pseudo-random for C with respect to D. And this notion of pseudo-randomness will pop up later in the talk, kind of in an interesting way. Okay. Also, like Rademacher, same thing happens by the way with like Rademacher complexity bounds. You can't estimate or test Rademacher complexity, so you can't actually use any of those bounds. I'll call them not useful bounds. I love Rademacher complexity. Right. So back to domain adaptation. Here's where we are, just to remind you. Now I can finally tell you like the model of TDS learning. So in this model, you run a test on samples drawn from D and D prime. And if the test accepts, then you are going to output a classifier whose error with respect to the test set is at most order lambda plus epsilon. And I will give you a proof, a certificate that your classifier does well with respect to D prime. Very strong guarantee, whenever the test accepts. Now, the interesting thing is, the test may reject, in which case, like, all bets are off. I'm not going to guarantee you anything. So that's not it. So we can't stop. Why can't we stop here when I'm defining the model?
Reject everything.
What?
You can reject everything.
Yeah, you could reject everything, in which case this is a totally trivial model. So the way that this becomes interesting is you have the condition that if, indeed, the marginal, let's just make it even simpler. If it's on X. If the marginal on the train equals the marginal on the test, then your test must accept with high probability. Okay, so your test can't just always reject. It has to accept sometimes. In particular, it has to accept when D equals D prime. That's the tricky thing. And it turns out to achieve all of this, you'll see is surprisingly subtle. Yes.
So you're basically saying if there's no shift.
If there's no shift, your test better accept.
But in all other cases it might.
In all other cases, it may reject, and you'll see how we can relax this to make it reject less.
Okay.
I'm going to talk about it. Okay, so let's just get a feel for this model. I really like this model. It is the correct model. Why is TDS learning more general than pack learning? Who wants to feel this one? Why is it harder to do TDS learning than pack learning? Why does TDS learning imply pack learning? This was supposed to be an easy question.
Because the distributions, we remove the distributional assumption that the test and training distribution.
Yeah, in pack learning, dtrain always equals dtest, but we just said the test has to accept when that happens. So in TDS learning, you're going to, if you want to pack learn, you can run your TDS learner. We know in pack learning, you're making this assumption, dtrain equals dtest, so you're going to accept, you're going to output a classifier with a proof that your error is small. Great, good. So the dream scenario, I think, would be to take every kind of result that we have for pack learning and extend it to the TDS model. And in some, like one avenue of research that my students and I have been working on has been precisely to do this. And it has resulted in a very kind of interesting and rich toolkit of algorithms that I want to give you a flavor for. Here's another interesting thing about TDS learning. Okay, it's a slightly more complicated problem, but in pack learning, there's this delta parameter, your parameter of failure. It's not the epsilon. We know that if you want to amplify the epsilon parameter, that's boosting. You know all about that. This is the easier thing. In pack learning, how do we amplify the delta parameter? How do we improve the confidence of our pack learning algorithm? Run it more than once. It's not fair. Run it more than once. Yes, exactly. So what you can do is you can run your pack learning algorithm. It gives you a classifier. And then you can just test. You can take more labeled samples and see, did my classifier perform well on these new samples? If it does, you output that classifier. If it doesn't, you just run it again. And so even if you only had a 1% chance of correctly outputting a good classifier, you're going to very quickly amplify it. It would have to fail every single time. So you amplify the probability of success of this classifier. Make sense? Okay, now notice in TDS learning, you have a problem. I run my TDS learner, it gives me a classifier, and then I want to check and see, did my classifier work? Well, I don't have any labeled samples from the test distribution, so what can I test? Yikes. So like so what you can prove actually is that if in TDS learning, if you're 51% confident, you have to start from something greater than 50%. So if you're 51% confident that your classifier is going to work, then you can indeed amplify it to 99% confident by taking a majority vote of many of the classifiers. And it's not like a deep result to prove this, but it is a sequence of like tricky averaging arguments. My point being that even this like very simple property of path learning, that you can amplify the delta parameter very simply, is actually non-trivial in the TDS case. Okay, so again, TDS is more interesting than path. Okay, I've given this talk a couple times, and I get questions like yours, which are excellent questions, so I have an FAQ. I guess they're just 3 questions, but okay. Why don't you just test that D prime doesn't equal D and just reject? What's the big deal, right? That's kind of what you're asking, right? Okay, so imagine that your training distribution is Gaussian, the marginals are Gaussian. And and then I'm going to take new samples from D prime, and I just want to say, oh, if it doesn't look Gaussian, reject, right? Yeah, this not even well defined. Think about it. If I take samples from D prime, how do I know if they're uniform over some discrete set versus drawn from some continuous Gaussian? Like the statistical distance could be 1, but how would I know? You could ask questions like, well, just test that they're far in Wasserstein or something. That takes exponentially many samples in the dimension. So what we take for granted is that even testing, like if you want to apply a result from distribution testing, good luck. Like these problems, because they're in high dimensions, are very difficult. Even testing these simple things like closeness to a Gaussian, exponentially many samples in the dimension. You can't do it. So there is no simple way of solving this problem. That's what's cool about it.
But if we just look at the top.
Hold on, we'll get to that. We'll get to that. Yeah, I mean, yeah, you see now like where the algorithmic ingenuity is going to have to come from. Aren't you going to reject all the time? Okay, well, yes, according to the model, we can reject almost all the time. But we have now like several results that really relax that. First of all, it's non-trivial even to do that, as I just said. Very non-trivial. But we have results that basically will only reject so now we have results that are tolerant. So if D and D prime are small with respect to variation distance, we have tests that will still accept. We also have tests that if D prime comes from like a very broad class of distributions, we call these universal, it will also accept. And the other thing I want to point out is that when you do accept, like you may accept, I don't know when, but whenever you accept, you get an incredibly strong guarantee. Like you get a proof that your classifier does well in the prime. And then I guess the third question is like, is this like learning with contamination? That's learning where an adversary comes and corrupts some fraction of your training set arbitrarily. It turns out that this is harder than learning with contamination. And we didn't realize this, but as we were coming up with these results, we can use the techniques for these TDS algorithms to solve like very long-standing open problems in learning with contamination. And we did that using the techniques that I'll talk about later in the talk. Any other questions I should add to the FAQ? Yeah.
So basically, D and D prime, you're looking at the raw data, right? You're not in the embedding space, right? Because if you go to
Raw data, yeah. Yeah. Okay, so let's do some more. We're continuing to warm up here. So let me give you a little puzzle to show you what kind of algorithms you need to run for TDS learning. These are toy puzzles. But here's a super simple case. So the class of functions that you're interested in are half spaces. These are functions of the form sine of w dot x plus theta. W is a unit vector. Theta is a real value. I know many of you have seen it. Assume lambda is 0. There's no noise. There's a ground truth function, labeling everything in dtrain and dtest correctly. And I'll even tell you that the training marginal on x is a spherical Gaussian. Okay? So you draw a bunch of training examples. And I want you to consider the scenario where you draw this training sample and every single label is +1. What would we do in pack learning if we got a bunch of labeled examples and their labels were all +1? What would we do? we'd output +1. We'd be like, oh, +1. The classifier that always outputs +1 is good, and you would be correct. But think about what happens in this model. Imagine that your training distribution is putting its weight all on these points here, they're all labeled positive. And now, how do I know? Maybe d-test is giving me some points over here. Or maybe it's still giving me points over here. What do I do? Like, even this case is now suddenly interesting. So yeah, this is my puzzle. Like, what should we do here? We see only positive examples in my training set. I see some new examples from d-test, but I don't see the labels. What should I do? Should I accept and say +1? Should I reject? It's paradoxical because it seems like we've learned nothing. We've seen only positive samples.
I have another related question. So here's an example with
So you have to solve this before you ask me.
So why can't you decide to accept or reject for specific sample?
We'll get to that. That's enough. You're stealing my thunder. It's another model I'll talk about in a second. That's called PQ learning. We'll get to that. I still have time. Okay, what have we learned? I know the students that I met know this because I told them. We have learned something about the ground truth. What have we learned?
Like theta might be very, like it's negative, right? So it's a very large.
You got it. It's positive. You meant positive.
Yeah, well,
You got it. You nailed it. Yes, that's the key observation. Very good. Theta has to be very large. Why? Well, W is a unit vector. X is a spherical Gaussian. So W dot X is normally distributed. The only way that I'm going to see all positive examples is if this theta value is so large that it overwhelms W dot X every single time. And the only way that can happen is if theta is large, something like much larger than root log whatever epsilon. Okay, so we actually have learned something. We've learned that theta is greater than, turns out you've learned it's greater than log, much larger than root log over epsilon. Okay, that's interesting. Any idea what we should do now?
Ground, like the actual edge, right?
We don't, exactly. We don't know W or theta. Well, all we know is theta is large now, but we don't know anything about W. So yeah, right. What do we do?
No, but we don't know even the format. There might be like.
No. We know the form. We know that it's sine of W dot X plus theta. That I said C is half spaces. I'm making this easy for you.
That's the length of the vectors in the prime.
You could try that. That's an interesting first attempt. That turns out to not work. What you end up doing is that you should check that D prime is somehow, the covariates are also sort of concentrated spherically. How do you check that? It turns out it suffices to estimate the moments of samples drawn from D prime. So for example, like we know that expectation of x1, x2, x3, if x is drawn from a Gaussian, there's like a simple formula for this, for what this quantity is. So what you do is you draw samples from D prime. Let's say the samples from D prime look like Z's. You compute the empirical moments of Z1, Z2, Z3 from my covariates on D prime. And you just check that it's very close to expectation of what it should be if they were drawn from a Gaussian. So for all degree log, it turns out what you should do is you should look at, expectation of Z1, Z2, Z3. You should look at well, I guess these are, should check that these are 0. Expectation of, all low degree moments. You can look at this. So you look at all of these moments of degree less than or equal to log 1 over epsilon. And you just check that they are what they should be if the distribution really was Gaussian. And what you can prove is that if all of those moments match, you get a concentration bound. And the concentration bound tells you that the covariates from D prime are nicely behaved. So that theta, if it's large enough, will still swamp out any contribution from W dot X. So if these moments match the Gaussian, you accept and you output plus. If the moments, the empirical moments from your D prime don't look like what they should be if they were Gaussian, then you reject. Okay, so the test here is to check that all of the low order moments actually look like what they should be according to the Gaussian. And what you end up getting from this is that you get a d to the order log 1 over epsilon TDS learner for half spaces in the noiseless case with respect to the Gaussian distribution. And in a subsequent paper, we actually proved an SQ lower bound showing that this is tight. You cannot do better than d to the log 1 over epsilon. Okay. Any questions on this? So you see how we sort of tested non-Gaussianity here. We checked low order moments. If one of them was not Gaussian, well, sure, then it's not Gaussian. That's a proof. We can reject. But when they are close, you can conclude some concentration properties of D prime. You can accept and output all plus 1. And you could ask, what happens if theta is not, what happens in the case where you don't see all positive examples in your training set? You have to do something else here. And so, you can use this approach, well, this particular approach, I'll talk more about it in a second, but, tell me your favorite like function class, half spaces, homogeneous half spaces, intersections of half spaces, decision trees, formulas, AC0 circuits. We have a bunch of papers that will come up with TDS learners for all these things. These results are actually outdated by now. But the main question the main like algorithmic question, and I think it's like the main fundamental question for learning with distribution shift, is this problem of, give me a classifier that you've trained on your training set. How can you certify that its performance will translate to T prime? What algorithms can you use? And as I mentioned, distribution testing a lot. And so another kind of simple thing that I want to show you, because it turns out to have a lot of applications, and I think it's very nice for many reasons, and it's related to pseudo-randomness. Is something about sandwiching polynomials. So what I'm going to show you is that if you have a function class that has sandwiching polynomial approximators, you can TDS learn it. You can learn it in this distribution shift framework. What's a sandwiching polynomial? A sandwiching polynomial for a function f is a pair of polynomials, p up and p down. And point-wise, these polynomials sandwich f. Okay, one's always less than or equal to f, one's always bigger than f. But the expectation of p up minus p down squared is at most epsilon. And furthermore, the degrees of these polynomials, let's always say that if they're degree k sandwiching, we say that they have degree k. Okay? Everybody okay with the sandwich? It's like, if you're familiar with like the bracketing number in statistical learning theory, it's somewhat related to this, except specifically it is for polynomials. So it turns out if your function class has degree k, L2 sandwiching polynomials, and we've been able to improve this to like the traditional notion, which are L1 sandwiching, and the moments of your training set sufficient to concentrate, then your function class is TDS learnable in time d to the order k. That much time and that many samples. And it turns out for half spaces, you'll get k equals order 1 over epsilon squared. And this works even in the noisy case where lambda is non-zero. Okay, so this is kind of the broad general theorem, like one of the simpler theorems that I can prove to you and show you for TDS learning. As I said, there are more sophisticated results that we have that I won't be able to get to today. And as I said, the algorithm again is to check moments. So if you have this sandwiching property, you just check that all of the low order moments match. And then you run polynomial regression with respect to the square loss, and you output h, which is the sign of p as the classifier. Yeah.
So are you not still doing some sort of distribution testing on the marginal on x?
Yeah, if you consider moment matching to be a distribution testing,
Right.
then you absolutely are. It is catered to these particular algorithms that I'm going to show you. Because the algorithm itself is polynomial regression. If you use a different algorithm, that test won't work. So the point is that the test has to be bespoke to the algorithm that you run. Furthermore, for more advanced results that we have, you cannot just run moment tests. You actually have to look at the labels on the training set. And though it's not clear how those really relate to distribution testing problems.
For any D, if I can come up with an algorithm that in polynomial time checks or polynomial number of samples, whether
Like,
I'm gonna cut you off only because I only have like 10 minutes left. I really want to get through all this stuff, so maybe we can talk after. Okay, thanks. Okay, so here's like the super trivial property I'm going to use, guys. This is really simple. If you have two distributions that moment match, we already said we can test that. And you have sandwiching polynomials, degree k. Then every time you see expectation of p minus q squared with respect to d, you can effectively replace it with expectation of p minus q squared with respect to d prime. It's just linearity of expectation. P minus q, quantity squared, expand it out, you'll get a degree 2k polynomial. All the 2k moments match, you use linearity of expectation, you're done. Okay, this is it. This is the transfer lemma we're going to use. Do you want me to prove this to you, or should I just skip this and move on? Skip? Okay, fine. This was proven so cool. Let me do it really fast. Okay. We want to bound this quantity, which is easy to see. It's less than or equal to the expectation of p, which is what you got from polynomial regression, minus f star squared. And then I'll use the triangle inequality. I'm going to add and subtract p down. This is prime, this is prime, this is prime. Okay, now here we have a sandwiching polynomial for f star. Right, so I can replace this, I can upper bound this by pd minus p up squared, because p up pointwise upper bounds f star. And then I can use my transfer lemma and switch this to d, because they 2k moment match. And then by assumption of the sandwiching polynomial, this goes to epsilon. Got rid of that term. Now we're left with this term. Again, p and pd are at most degree k. So I'm going to switch to expectation of d, p minus pd squared. I can do that because I'm a moment matching thing. Now I actually have to add and subtract back in f star. Okay, and then, but here I can replace it with p up, because it's a pointwise thing again. This goes to epsilon. And here I have expectation of p minus f star squared, but p, we got p by using polynomial regression. We knew p was the best fitting polynomial. So in particular, it's better than p down. It fits better than p down. So it's upper bounded by however p down does. But then I have this p up again for f star, and this goes to 6. So you play a bunch of triangle inequality games. And that's it. That's the proof. It works. Okay, did it really fast. And then you can just start asking, well, what function classes have L2 sandwiching polynomials? And you get a bunch of function classes. Turns out we can relax this to L1 sandwiching, so we get all of AC0. Okay, I have time to mention a few of these are the easy results. I have time to mention a few of the harder results. So if your class of half spaces is origin centered, you actually can achieve fully polynomial time instead of that d to the log whatever epsilon or d to the 1 over epsilon squared. And the high level outline, like this, I like this because it's like the most complicated half space learning algorithm you've ever run, is you run SGD on a non-convex loss that Dan Kane and Ilias Nicholas and collaborators came up with to obtain some initial candidate. And then you have to test some weak anti-concentration and concentration properties around this candidate. It's related to, you can run some SOS tests to do that. And if they all accept, you accept and output whatever this algorithm gave you to work. The idea, I'll just skip this. The idea is that it's called localization. So if the ground truth is this F2 half space, and the algorithm that non-convex SGD that you ran gave you V1, you get this error region shaded. And the question is, how do I actually run a test to know that D prime, the test distribution, doesn't put too much weight on this error region? And it turns out that what I have to do is test various spectral properties of a projection matrix that only depends on V1, the classifier that I actually put. So in this case, I actually have to look at the labels of the training set to get V1, and then come up with a test that's catered to that specific classifier that I output. In particular, the classifier output by Ilias and Dan and Christos and Nikos' output. Then we have a notion of localized discrepancy distance, which I'll skip over. Here's what I want to do. So tolerance. So we wanted to come up with algorithms where you accept even if the TD distance between D and D prime is at most epsilon instead of being equal. This was first done in a paper by my students Sergey Govel, Abhishek Shetty, and Kostas and Arsen. And it's very related to PQ learning, which you asked, which is a model where you want to accept or reject more granularly on each particular data point. Like instead of saying I just globally reject, you want to come up with points in your test set and say, I will label you, I will label you a question mark, I will not label you, et cetera, and so on and so forth. And the way it works, the main technical idea is to use outlier removal. But it's a different type of outlier removal. It's an outlier removal algorithm that that preserves the expectation of all squared polynomials. So what the outlier removal algorithm does is it outputs a selector function, G. Selector, if it's 1, it means include this point. If it's 0, it means don't include this point. And it has the following nice property. If you look at the expectation of the test set for any low degree polynomial P, if you look at expectation of the test set of P squared times G, so you're going to do some removal of points in D prime, as indicated by G. And then you look at the expectation of the square of any polynomial on the resulting kind of filtered test set. It will actually be close to its expectation with respect to the training set within this factor over alpha. And the number of points that G throws out on your test set is actually going to depend only on the TD distance between D and D prime. And that's why you start getting this tolerant property, because the number of points that I throw out is only dependent on the TD distance between D and D prime, and it ends up preserving the squared norm of these polynomials. And as you can, you can kind of at a super high level, because I did the proof that you all wanted me to skip. Now every time we see expectation of D prime of some polynomial, instead of just shifting from D prime to D, well, we can shift from D prime to D, but at the price of this 1 over alpha P squared. But then you play more triangle inequality games, and things tend to work out. So how do you come up with this outlier removal algorithm that preserves these expectations? That is a whole other topic. We use this to solve some long-standing open problems for supervised learning with contamination. So the unsupervised learning with contamination, like robust statistics work by Dan and Ilias and others, people have heavily studied that problem. But the supervised case has been really has been left open. So by supervised contamination, what I mean is that an adversary comes, removes an eta fraction of your training set arbitrarily, and replaces it with some other eta fraction of points and labels. And the goal is to output H such that the probability that H is far from the ground truth is at most 2 eta plus epsilon. 2 eta is the best that you could hope for. And basically what we do is we run that outlier removal algorithm on just the training set. It preserves all of these non-negative polynomials, and it turns out what we first proved is that for any function class that has sandwiching polynomials, you can learn them in this contaminated setting. So you get AC0 learning with contamination that have been open for decades. We have this at COLT 2025. And then the super surprising result to me was that it turns out that if you have a function class, you don't need sandwiching. So if you just have a boring old L2 approximator for functions in your class, they can be learned with contamination efficiently up to the optimal error rate. And this is surprising because, this result that I came up with at TTI 20 years ago, we were only able to get tolerance to label noise. And it turns out this will appear in Europe, so what we were able to prove is that in addition to getting label noise, you actually get, you get learning with contamination for free. You get this much stronger guarantee that we didn't think was possible. Then we have some other things. I'm out of time. We can compose our results with testable learning, if you've heard of that. Universality, we can accept a large class of test distributions under some mild conditions. My concluding thoughts are that this TDS learning makes use of a really wide array of techniques and recent TCS developments. Traditionally, pack learning has relied on the Fourier method and boosting and kind of nothing else to come up with efficient algorithms. And so what I like is that we've had to rely on a lot of rich and interesting techniques. to come up with new algorithms. As I said, I believe epsilon delta learning is sort of mimicry. Domain adaptation is a more meaningful notion of learning. And yeah, I just want to remind you that assumptions like undermine, the value of our provable results. So I'll stop here. Thanks.
We have time for maybe a couple of questions.
So your algorithm requires the data distribution for the training and the test at least has some similarity close in your sense?
No,
No.
you can reject it so far.
Yeah, but you need to like the moment to match in some sense, right?
If you want to accept, yes.
Yeah. So what we can do? What can we do if it rejects?
Nothing.
that?
But it would be amazing if you had an algorithm. Think about a language model. If the language model could tell you, I'm not confident in what I just output, that would be awesome.
Yeah.
Yeah, I was just gonna ask, so it seems like in this context, you kind of assume that the cost of sampling from the D and D prime are roughly the same in order to be able to test, moment match and so forth. But like in context where you have online data, like that's not exactly the case. So is there like some kind of model that makes sense for online learning?
Yeah, that's a great question. I mean, so two things. First of all, for not only do we not make assumptions on the test set, we don't even need the assumption that the test set is drawn from a distribution. It can just be an arbitrary set. But in terms of online learning, see, the problem, I talked with a little bit about this. I mean, the issue is that in all the online learning results I'm aware of, you always get to see like a label with the next point. So I sort of don't know maybe there is a right way of doing it, I just don't know where to begin. Go on.
Yes, so you started with the biology example. What does this method say for application? Just it always rejects, or?
Yeah, good. So I don't know how to take these, like especially the moment matching results. I don't know how to take those and import them into protein engineering. I will say that we did come up with a different notion of a different metric that does seem to produce proteins that move out of distribution. We had to do a different type of regularization. Was it like directly inspired by a technical thing here? No. But like I said, I mean, I think the foundations of hack learning, for 50 years, we've had thousands of papers. Yeah. I'm just trying to figure out what we can do here. Yeah. Oh, hold on, yeah, go ahead.
Just a question.
Okay, last question. We can talk offline.
There is time.
One of the motivation at the top was that you have like two images, and in order to get like the images that come from D and D prime, if you use like Wasserstein or those kind of nouns, you need like a lot of number of samples in order to approximate that. But in your new method, how does that apply here? Because this moment matching might not actually be possible when you're dealing with the images. And also, I don't understand like the condition you had that you had to sandwich it between two polynomials.
Oh, I mean, yeah, those are conditions under which we can actually develop like provably efficient algorithms. They may or may not hold in practice.
So is there any like practical like result?
Not yet.
No.